Hi guys! Welcome back to yet another episode with Moments with Chemistry. So today we're going to continue our long felt MCQ paper discussion, and today we're going to start up with the A-level 2018 chemistry paper. So this has been after a long lapse of time, so I hope you enjoy this video. Okay, question number 1. The number of unpaired electrons present in a gaseous cobalt-3 plus ion in its ground state. So you know that cobalt, if you have properly memorized the periodic table, cobalt has an outermost electronic configuration of 3d7-4s2. So if it has to be cobalt-3 plus, 3 electrons from the outermost shell should be removed. So here 2, and from 7 we had to remove only 1, giving it 6. So if you draw the diagrammatic representation of this d orbital according to Hund's rule, first of all they have to fill singly before pairing up. 1, 2, 3, 4, 5, 6. So these are the ones that are unpaired. So the number of unpaired electrons is 4. Cobalt 3 plus has only 4 unpaired electrons. So for question number 1, your answer will be answer number 4. Question number 2. Which quantum numbers NL, ML, MS are associated with the shape of an atomic orbital of an atom? You know that N is the principal quantum number. It depicts you which energy level the particular electron resides. Then L, the azimuthal quantum number. It gives you the type of orbital that houses this particular electron, whether it's an s orbital, whether it's a p orbital. Then ml gives you the suborbital. Within let's say for example, within the p orbital you have 3 other, within the p subshell you have 3 other orbitals, right? So the name of the orbital is given by ml, and ms is your spin quantum number, which gives you the direction in which the electron revolves. So, associated with the shape of an atom, actually it's L and ML. Now, L is azimuthal quantum number. It gives you the type of subshell. So, if it is S, it should be spherical. If it is P, it will have to be dumbbell. And if it is D, it will have some other odd complex shape. And this is in terms of L, azimuthal quantum number. In terms of ML, still this will be spherical. Although this is dumbbell, it will have an orientation in 3 planes of space for P. And for D, obviously a more complex feature. So answer for question number 2 will be answer number 5. Okay. Question number 3. Correct IUPAC name. Correct IUPAC name for this particular compound that has been given below. For this particular compound. Okay. CH3, CH2, CH, Br, CNO2, CNO2 double bond, CH, COOH. So we know first of all we have to identify which is the longest carbon chain. So the one that runs laterally will become your longest carbon chain, and we have to give the lowest number, or we have to give the highest priority to the functional group. Functional group is carboxylic acid. So 1, 2, 3, 4, 5, 6. Then you have to identify what are the substitute groups. We have bromine and NO2. Now we have to write the name. And we have to write the name according to alphabetic order. So it will be 4 bromo 3 nitro hex 2 enoic acid. Hex 2 enoic acid. The first one, according to the English medium, according to the English medium, it's the second one. Because between enoic and acid, you will have a space. That is why the first one has been rejected. Between these two, there is space. So 4 bromo, 3 nitro, 2-hexenoic or hex-2-enoic acid. So for the English medium paper it will be 2, but for some other reason they have given it as all. Okay. Question number 4. The correct answer when molecules oxygen, water, hydrogen peroxide, OF2 and OF2 arranged in decreasing order of the oxidation state of oxygen. This is nothing. O2, oxidation state of oxygen is 0. In water, oxidation state of oxygen is -2. Then in H2O2, if I consider oxygen to be X, plus 2 plus 2X equal to 0. So X equal to -1 in H2O2. Then in OF2, you know that fluorine always carries -1 charge, so this is +2 oxidation state, and O2F2 will be obviously +1, half of this. So the highest one will be OF2, then it will be O2F2, then it will be O2, then it will be H2O2, then it will be water. So your answer for the fourth one will be answer number 4. You just have to get the oxidation state, and once you get the oxidation state, just put them according to the ascending order. That's it. Most acceptable Lewis structure for the thiocyanate ion. You know, when a Lewis structure has to be considered as most suitable or most stable, there have to be certain priorities, or there should be certain criteria that have to be fulfilled. Number 1, the most electronegative atom should carry a minus charge, or the less electronegative atom should carry the positive charge. Two atoms with the adjacent charge is not that stable, and the charge separation that is vested on one atom should be minimized. Okay. So if you consider the thiocyanate ion SCN2 minus, SCN minus. So from this you have to judge who is the one with less electronegativity. It's obviously nitrogen. So whatever we do in our most acceptable Lewis structure, we have to try to avoid the negative charge onto this nitrogen atom. So if I give negative charge to this nitrogen, it should surely carry a double bond. So the total number of electrons 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6 minus. I think this should give you a good answer for SCN minus. So your answer for question number 5 is answer number 2. Question number 5, your answer will be answer number 2. Question number 6. The molarity of an NaI solution with density of 1.03 grams is 3% NaI by mass is. Okay. So we have a sample of NaI. And within that sample, not the entire sample has NaI. Only a certain proportion of the sample has NaI. And the corresponding percentage for that sample has been provided to you. Okay. Now, we have to find the molarity. What is molarity? It is a method with which we can express composition of a given solution. Moles over the volume. Okay. But you know that, what is density first of all? Density is the mass of a particular substance in 1 cubic centimeter. So you know that mass of NaI in 1 cubic centimeter will be 1.03 grams and 3% of that. Okay, that's okay now. Then number of moles of NaI in 1 cubic centimeter. You know the mass, so if you divide it by the molar mass, you have to be able to get the number of moles of NaI in 1 cubic centimeter. So iodine is 127 and 23. 150 gram per mole is the molar mass of NaI. So the NaI concentration, what is concentration? The number of moles of NaI that are present in 1000 cubic centimeter, that is 1 cubic decimeter. So that's going to give you 1.03 into 3 over 100 multiplied by 1 over 150. This is there in only 1 cubic centimeter, but we are interested with 1000 cubic centimeters. So 1, 2, 3, 1, 2, 3. So this is going to give you 5. So this is 0.206. Yeah, 0.206 mole per cubic decimeter. So since all your answers are given only to 2 decimal places, I'm going to round this off to 0.21 mole per cubic decimeter. This has been actually tested in a lot of past papers. So if you do the past paper, you can do this like in one step itself. You can write the equation and then it's just a matter of doing your simplifications. Okay. Okay. So that's 6. Your answer should be answer number 1. Okay. Now question number 7. That is something to do with KSP and equilibria. Right. Precipitates of AgI and AgBr were added to a small amount of distilled water. So you have distilled water and you are adding the precipitate of AgI, AgBr. This mixture was allowed to reach equilibrium at 25 degrees Celsius. It was observed that both the solids were present in the system at equilibrium. So at equilibrium we have both AgI and AgBr, okay, within your solution. Which of the following reactions, which of the following relations is applicable to this situation? KSP of AgI given, KSP of AgBr. Now we will find, what is this, we will find this one by one. Separately for AgBr and then separately for AgI. But we have to know that as per the question, they have given us that both the solids are there at equilibrium. Okay. Now I am writing the KSP expression for what? First AgI. So AgI solid reversibly giving you Ag plus aqueous plus I minus aqueous. So KSP equal to Ag plus aqueous concentration into I minus aqueous concentration. So this is given 18 to 10 to the power minus 17 mole square dm minus 6. Then if I consider this to be x, this also will be x. So this will be x squared, if I'm not mistaken. X squared. Considering Ag plus from I minus is bigger. But if you consider AgBr solid giving you Ag plus aqueous plus Br minus aqueous. So we'll consider it like this, will you? I minus aqueous concentration equal to 18 to the power minus 7 divided by Ag plus aqueous concentration of the solution. This Ag plus aqueous concentration is what is there in the solution, because everything is together. Here also if I consider KSP equal to Ag plus aqueous concentration multiplied by Br minus aqueous concentration. So here KSP value is given to you, 5 into 10 to the power minus 13. Ag plus is whatever is there within our solution into Br minus aqueous concentration. So Br minus aqueous concentration equal to 5 into 10 to the power minus 3 divided by Ag plus aqueous concentration. Okay. As you can see here, I did not consider the concentration of Y minus and Ag plus to be equal. Why? We are not particularly sure whether this particular solution has attained its saturated level. So therefore, since Ag plus serves as a common ion, giving a common ion effect for both of them, I just consider it to be Ag plus. So somehow or the other, mathematically we should be able to get. Now if you look at this, first answer, it gives a direct, what does it give? It gives you a direct mathematical value for Br minus, but that's not going to work. Br minus I minus equal to Ag plus square. Okay, we'll see that. If you multiply these two, you should get 5 into 10 to the power minus 3 into 18 to the power minus 17 divided by Ag plus square. So even if you multiply, Ag plus should come onto the denominator. Ag plus, you know that whenever we do equilibrium, we don't consider this plus. So therefore, it should be omitted. Now look at the fourth one. Br minus divided by I minus. Look at these two equations. Br minus divided by I minus. So Br minus value is 5 into 10 to the power minus 3 divided by Ag plus aqueous concentration. That should be divided by I minus 8 into 10 to the power minus 17. Up you are going to get Ag plus aqueous concentration. Here Ag plus cancels. So this is 5 over 8 into 10 to the power. Sorry, this is 5 into 10 to the power minus 13. So this is also 13. So 17, 13, 14, 15, 16, 17, 10 to the power 4. So this will be Br minus over I minus concentrations. So your answer should be answer number 4. For question number 7, your answer will be answer number 4. Alright, question number 8. Which of the following statements is false? This is a statement question. You should be able to do it rapidly fast. Right. Although carbonates of all group 2 metals in the periodic table are insoluble in water, their bicarbonates are soluble. No. Group 2 carbonates exist in the aqueous phase. Group 2 carbonates, whatever the group 2 carbonates that we have, they exist where? In the aqueous phase. Okay? Sorry. Although the carbonates of all group 2 metals in periodic table are insoluble in water, bicarbonates are soluble. That's correct. Because bicarbonates have the ability to dissolve in water for group 2, while the carbonates are not going to get soluble in water. So that's correct actually. The hydroxide of all group 2 metals in the periodic table are soluble in water. No, magnesium hydroxide is going to give you a hazy solution. Sparingly soluble. The nitrates of all group 2 metals in the periodic table, are soluble in water, correct? Nitrates, then chlorides, nitrates, nitrites, all of these are always soluble. X minus, where it is a halogen. The oxides and hydroxides of sodium and magnesium show basic properties. Sodium, magnesium, metals basic, okay. And the hydroxide of aluminium shows amphoteric properties, correct. Hydrides of sulfur and silicon show weakly acidic properties. Sulfur weakly acidic is correct, but for silicon it's not weakly acidic. SiH4. 5. Question number 8. Answer will be answer number 5. Okay. Now we'll come on to question number 9. In which list are the elements given in the order of increasing atomic radii? Now you know that if you consider a particular period from left to right, the number of shells doesn't change. But the number of protons that are vested within the nucleus increases. So therefore, the attraction between the nucleus and the outermost electron increases. Thus, the atomic radii decreases across a period. Down the group, what happens? The number of shells increases. So therefore, the atomic radii should increase. Right. We look at them. Look at the first one. Lithium, sodium, magnesium, sulfur. Lithium, sodium, magnesium, sulfur. From left to right, it should increase. Which means the least one should be on the left and the largest one should be on the right. Either. Okay. Now, lithium, sodium, magnesium, sulfur. Now, you know that lithium is someone who belongs to group period 2. Okay, lithium. Sodium and magnesium belong to period number 3. Sulfur also belongs to period number 3. So, if you look at their order, lithium is the smallest, then it should be sulfur, then magnesium, then sodium. So for the first one, this should have been the answer. Okay, second one, carbon, silicon, sulfur, chlorine. You know, silicon, sulfur, chlorine, all of them belong to the third period. And carbon is second period. So carbon, least one. Now between silicon, sulfur, chlorine will be the smallest one. Then sulfur, then silicon. Okay, third one. Boron, carbon, nitrogen, fluorine. You know, boron, carbon, nitrogen belong to period number 2, but phosphorus is for the next period. So nitrogen will be the smallest. Okay, nitrogen will be the smallest. Then carbon, then boron, then phosphorus. Third one. Fourth one, lithium, sodium, potassium, calcium. You know that potassium, calcium belong to one particular period, the third period. Potassium and calcium belong to the fourth period. Sodium belongs to the third period. Lithium belongs to the second period. So, lithium, sodium, calcium, potassium. Look at the last one. Boron, beryllium, sodium, K, potassium. Potassium is for period number 4. Potassium is for period 4. Sodium period 3, beryllium, boron period 2. Okay. Boron is from period 2. Okay. Beryllium is from period 2. Sodium is from period 3, potassium from period 4. So, boron will be the smallest, then beryllium, then sodium, and finally K. So this will be your answer for question number 9. So for question number 9, your answer is answer number 5. Okay, question number 10. Liquids A and B form an ideal solution. Consider a mixture of liquids A and B in equilibrium with a vapor in a closed rigid container at constant temperature. P0 A and P0 B respectively are the saturated vapor pressures of A and B, while P is the total pressure of the container and X0 XAG is the mole fraction of A in the vapor phase. Okay, is the mole fraction of A in the vapor phase. Now, separately for A and B, I am going to apply Raoult's law. So, PA equal to P0 A into XA. Okay, PA equal to P0 A into XA. PB equal to P0 B into XB. Okay. And assuming ideal behavior for the gaseous phase, P equal to PA plus PB according to Dalton's law of partial pressure. And PA equal to PT into XAG. Partial pressure of A equal to total pressure of A into the mole fraction of A in the gaseous phase. Okay. Now, instead of PA for this equation, I am going to substitute PT into XAG equal to P0 A into XA. So, from this I can get XA equal to PT into XAG divided by P0 A. Okay. XA equal to PT into XAG divided by P0 A. Okay. Now, PB equal to pressure total into 1 minus XAG. That's okay now. Since in the gaseous phase we have only A and B, if the mole fraction of A is XAG, mole fraction of B will be 1 minus XAG. PV is also okay. Now I am going to come and substitute to this equation. So P0 B, what is XB now? 1 minus XA equal to PT or P into 1 minus XAG. Okay, now P0 B minus P0 B XA equal to P minus P XAG. Okay, so P0 B minus P0 B into XA. Instead of XA, I am going to put this P, it's P, P into XAG divided by P0 A equal to P minus P XAG. Okay, P minus P XAG. Same thing, P naught B, I take P naught A common factor, or let it be like that, P naught B minus P naught B P XAG divided by P naught A. So if I take 1 over P from this equation, okay, 1 over P, I have to take P here, 1 over P equal to, before taking 1 over P, we will try to solve this, then it will be easy for us. P naught A, P naught A, P naught B minus, so if I take 1 over P here, I have to take the P naught A up there. So P naught A minus P naught A XAG divided by, from this upper equation, okay, we say it as P naught A, P naught B minus P naught B into P into XAG. Now there are certain common factors that you can take. You take P naught B out and divide separately. Okay, we take P naught B out and divide separately. So if I take P naught B out, it will be here up, P naught A by P naught B minus P naught A XAG divided by P naught B, okay, minus P naught B. This will be divided by P naught A minus P XAG. Okay, what did I do here? I took the P naught B common out and divided it. So P naught A by P naught B minus P naught A XAG divided by P naught B into 1 over P naught A into minus P naught B XAG. Okay, now look at our questions, answers that are given. We had to try to get 1 over P naught A minus 1 over P naught B from this entire equation. Okay. 1 over P naught B minus 1 over P naught A. Okay, I'm just taking 1 over P naught B and taking this other side up and down. Then it will be multiplied by XAG plus this P naught B should go up, P naught, okay, no, it should not go up, it will be in the same place, 1 over P naught B. 1 over P naught B minus 1 over P naught A into XAG plus 1 over P naught B. This is the answer for 1 over P. So your answer for question number 10 is answer number 2. Question number 10, your answer will be answer number 2. So this marks the end of our first session with 2018. Hope you enjoyed and hope many of you all had got to know new knowledge, and see you in the next video. Thank you.